Hi, it's Terry Dennery of the MathWorks. So this is this robot. I've had it for a long time, and we've done lots and lots of good seminars with it at MathWorks. And I think on YouTube there's there definitely is a video called "Model-Based Design of Control Systems." It's got something like 50,000 views that my buddy Sam Mirsky and I put up there probably like 10 years ago. And anyways. I wanted to return to it. I've always liked this demo for a lot of reasons, um, but in this series of videos, I want to really emphasize this point: mechanics first. Okay, and the basic idea is that what it is. That's the thing that's going to really do things. It's the mechanics that will grip things and move them, and all that mass and inertia and geometry really is going to set the requirements for everything about that system. There's a lot of other stuff in that system, and so it'll lead to your electric motor choices and how you're going to control it and all kinds of stuff like that. So that's our basic idea. So let's kind of look at this simulation. Let me reset it and we'll watch it. So we got it moving very fast, by the way. I think those turns are something like 0.2 of a second. I love this. Are you seeing that? Let me reset that a little bit. So it does this last little move. And I love the rattle. And it might be too subtle, a little too hard to see, but that's why I recorded the measurement in that scope right there. And you'll see right here, yeah, that, okay, see that? It's Z is up, red is X, and Y kind of goes in and out of the screen. But it's both the Z and X component have a measurable variation. It's about 0.5 millimeter for each of them. All right, and why is it there? Well, this is rigid body dynamics, so it's not the parts bending, okay? But let's just kind of get at the top level and kind of look at a few things, all right? And so this is the model. You'll see it's, what I really enjoy doing is showing SimScape multi-body. That's how we got it here. And you'll see all kinds of bodies and joints and stuff like that. But let's, again, kind of get onto the topic of where's the compliance, right? And it's that we're modeling the electric motors as well, all right? And so you'll see from SimScape Electrical, we got the 3-phase permanent magnet synchronous motor. We have a field-oriented control algorithm that's going to take kind of the commanded torque and implement it through that motor, right? Okay, so that's some compliance there. And then we have controllers, all right? And so our controller, it's going to be made up of kind of a network of feedback and point PIDs, and then there'll be a feed-forward piece too, which will take kind of our intended motion and figure out what the torques are required to do that based on what we call an inversion of the mechanical equations of motion. All right, and so anyways, you'll see my PID. I'm not giving it a whole lot of thought. It's really just P, and I just chose the value of 10. And if you know a little bit about PIDs, you know that Kp is sort of like a spring constant. So I'd say it's somewhere in there that we got a little bit of the compliance. While we're here, let's show the feed-forward algorithm. So we're telling it how we want it to move. We're telling it in terms of position, velocity, and acceleration for each of your motors or your actuators. And from that, we're going to see about 1,000 lines of code that are going to do that calculation to figure out these quite important torques that we're going to see in lines 1078 through 1082. All right, so I think I'll wrap up on this one because this is our introductory video. Just showing that we're also doing I'll call it a validation. We're comparing two mechanical models. And so that same method of generating equations of motion, well, we have both the forward dynamics as well as the inverse dynamics. Here's the forward dynamics. What we were looking at before is the inverse dynamics. Okay, and I'll just say that both, I'll give a little bit of a shout out to, well, first of all, Motion Genesis, the tool that took that same mechanical description and turned it into lines of code. And I'll give a shout out to my buddy Paul Mittigi, who made sure Motion Genesis is there. So anyways, as we kind of look at our validation, this is one of those axes that don't move, but you'll see the agreement is taking place at like 10 to the minus 5 on that one. And so let's look at one of the ones that moved. Here's the forward actuator. And again, you're seeing a little bit of that oscillation, but we're seeing a good validation between the two. All right. So anyways, it's kicking off a series. The series can be called something along the lines of mechanics first. And, you know, it should be fun. I hope you enjoy it. Thank you.